It arrived from the deep, silent and frigid, a loner crossing the dark. As it swept past the sun, 3 Atlas did what no ordinary comet does. It sped up. Not from gravity, not from gas jets or the solar wind. It pushed itself. Fresh NASA analyses say the effect is real. An unseen force working against gravity. Months earlier, Avi Loeb said this moment would come. He argued it might be a relic, a shard of engineered hardware, maybe a dead probe, maybe a light sail drifting through our system. Many called that impossible. Yet the figures keep stacking up. If first contact begins, it may not be a greeting in radio. It may be a small change in speed, a quiet signal written as numbers. Stay with the story. What follows could be the strongest hint yet that we are not alone. If this puzzle has you on edge, subscribe, share your thoughts and where you are watching from. Spread the word if you want more work like this to continue. Breaking news. Imagine the first technological signature found not on Earth, not in orbit, but out between Mars and Jupiter. An artifact gliding through our neighborhood that we almost failed to notice. This is not fiction. This is orbital dynamics and instrument data. It is unfolding now. On October the 29th and 30th, 2025, the interstellar visitor catalogued as 3 Atlas reached perihelion. For ordinary comets, perihelion is routine. You add up the pulls, include solar wind effects, and watch the track behave. 3 Atlas broke pattern. The object accelerated beyond what gravity explains. JPL, using Punch's Wide Field Imager 3, measured a radial acceleration near 135 km per day squared, pushing away from the Sun, and a transverse component near 60 km per day squared. In plain terms, a force not tied to gravity or known outgassing is at work. Loeb had flagged this possibility. He is known for proposing that Oumuamua might have been a light sail fragment. That view drew heat. He countered that rare data demand open minds. With 3 Atlas, the anomalies stack higher. Brightness rose fast. Too fast. The photometry follows an inverse power law near -7.5. Typical comets sit closer to -2 to -4. Translation. This object brightened at a rate models do not predict for sun-warmed ice and dust. The color is odd as well. Instead of the usual neutral to red tones, 3 Atlas skews blue, hinting at fine dust or reflective surfaces that behave more like metal than dirty snow. So the question hangs. Is 3 Atlas a piece of technology? A dead probe? A torn sail? A vehicle making a planned move at our star? If yes, what follows? Because if one object is artificial, our priors about every faint wanderer change. How many close passes have we waved away because the alternative felt uncomfortable? We will show the data and the arguments. The plans for new looks. What those looks might confirm. First, how firm are these claims? We need the measurements, the instruments, the people who flagged the deviations, and the teams testing the fit. This is not settled. Researchers are split. Some intrigued, some dismissive, a few uneasy. Not due to fear of aliens. Due to the simple fact that we have no playbook for this. No protocols. Few telescopes were ready. The pivot point came from Punch's Imager. It was built to watch the corona and solar wind, not to hunt artifacts. Yet it had the right field at the right time. A JPL navigation specialist stacked frames, tracked the path, and found motion that gravity alone does not match. Radial near 135 km d squared. Transverse near 60 km d squared. Over weeks, such small daily pushes move an object tens of thousands of kilometers. That is big in trajectory space. 3 Atlas passed the Sun at about $1.36. Farther out than Earth's orbit. Warm enough to matter, not hot enough to strip it bare. Comets near the Sun vent gas. That thrust nudges their paths. We can model it, and often do. But here the acceleration appears without the expected outgassing signatures. No clear jets in the images. No strong coma or lines strong enough to carry the needed momentum. That mismatch drives the debate. Photometry shows the steep brightening law. Early spectra caught carbon dioxide far from the Sun, which fits a comet rich in CO2. Near perihelion, water should have surged. Some water shows, but not at levels that explain both the speedup and the light curve. Taken together, the trajectory, brightness, and spectra point to behavior our standard comet models do not capture. Skeptics remind us that models rest on assumptions. Mass, albedo, spin state, surface heterogeneity, dust sizes. Change the inputs, shift the outputs. That is fair. Science advances by tightening assumptions, not by jumping to grand claims. Still, the deltas are large. And the next observing windows in November and December were set to cut through the uncertainty. Two frameworks face off. Natural outgassing versus engineered force. Loeb's argument begins with mass loss. To reach 135 km d² outward acceleration through venting, the mass flow must be high. That should light up the coma and spectra. Instead, we see modest gas. The color adds tension. Typical comet dust reddens the reflected light. 3 Atlas trends blue, which fits very fine grains or reflective surfaces. Neither is impossible in nature. The combination with weak gas is the rub. If this is a sail, sunlight does the pushing. Radiation pressure at $1.36 is lower than at $1 yet still non-zero. A structure with high area to mass and high reflectivity could feel those photons and drift measurably. Ultra-thin, highly reflective, low density. Achievable for engineered materials. Rare in nature. A tumbling, torn sheet could also explain odd photometry. Another path is a powered assist. Real missions fire near closest approach to multiply the effect. Chemical burns long enough to matter need too much propellant for this mass regime. Low-thrust electric systems could shape the path over days if power remains. No clear thermal or exhaust signature is seen, but our instruments were not tuned for that. Exotic drives live in speculation. We keep them in the bin marked unknowns, not as claims. What breaks the tie is data. November flyby geometry for JUICE offered a long shot at spectra or imaging. December slots for Hubble and JWST promised deeper looks. If strong outgassing shows, nature wins and 3 Atlas becomes a weird yet natural comet. If the acceleration persists without matching gas, the artificial hypothesis gains weight, and the conversation expands from mechanics to intent. Institutions walk a narrow road. Some claim key images have been delayed. Hiris on MRO was mentioned by name. The lack of a clear response fueled commentary. Bureaucracy and calibration can explain slow releases. Silence breeds suspicion. In parallel, IAWN launched a coordinated campaign through January to pool observations. Routine for unusual targets, yet a signal that agencies take this seriously. Public attention shifted fast. A niche object became a cultural flashpoint. Trust sits at stake. If evidence leans toward artificial, policy actors will enter the room. SETI groups will weigh in. Mission concepts will move from slides to studies. The stakes demand care, openness, and rigor in equal measure. Trajectory context frames the scale. Interstellar objects roam the galaxy on hyperbolic paths. Oumuamua and Borisov showed the range. 3 Atlas comes in fast, on a steeply inclined track. Its origin is uncertain once you run backward past the planetary region. The history smears with small errors and long times. If engineered, it may have drifted for ages. If so, speeds above our probe's records imply either better propulsion or time on a sail. Comparisons help. Comet C 2025 R2, Swan, behaved by the book. Strong gas. Tail. A brightness law near -3. Color near neutral to red. 3 Atlas diverges on each of those axes. One odd trait can fit a natural edge case. Several at once invite closer work. Brightness behavior holds more clues. A -7.5 exponent is steep. Fine dust could raise scattering efficiency. Rapid surface change could expose fresh reflective patches. Both require activity that should show in gas and dust. If not, we face a surface with properties unlike common icy bodies. Metallic facets would reflect strongly and could skew color blue. A tumbling, paneled object could yield fast light swings without strong gas. Conspiracies grow in gaps. Data pipelines are slow by nature. Instruments not built for this target yield grainy frames. Releasing low senior images feeds doubt. The cure is not a flood of raw bits. It is context, calibration notes, and fast independent checks. Assume artificial for a moment. What could it be? A sail fragment. A thin, reflective sheet with high area to mass. Micrometers thick. Pitted by dust. Torn by impacts. Still responsive to light. Or a craft with a fading power source and low thrust capability. Or a shell with materials that mimic metals in spectra yet sit below detection limits at current senior. JWST could spot thermal excess if an internal heat leak exists. Hubble could sharpen coma and dust constraints. Metallic lines would be a strong clue, though weak and blended features are hard to pull from noise. Purpose remains the hard question. A survey probe. A derelict. A node in a dispersed network. We do not know. Any design that survives interstellar space must beat radiation, thermal cycling, and micro-impacts. That points to robust construction or recent origin. Implications ripple outward. The Drake equation reminds us that many stars and planets exist. The Fermi question asks where the others are. If artifacts pass through often and we seldom recognize them, the answer could be simple. We were not looking the right way. SETI has mostly listened. Technosignature work now expands to searches for objects and waste heat. Loeb pushes for that shift. Critics demand stronger evidence. Both pressures improve the science. If confirmation tilted artificial, policy and culture would move fast. Security questions. Mission proposals. International coordination. A surge in funding for searches and intercepts. Faith traditions and philosophies would process the news in different ways. Risk scholars would ask about intent. Most likely outcomes remain non-threatening. Distance, time, and degradation work in our favor. Still, the need for clear protocols is obvious. Elsewhere in the sky, the Draconids offered a control case for dust dynamics in October. Models predicted an outburst window and reports matched. Those successes validate our grasp of dust under solar radiation and gravity. When an object refuses to follow those rules, we take notice. Large surveys are changing the game. Instruments like Foremost feed millions of spectra into public vaults. Wide coverage finds outliers. AI systems sift the stream, flagging the rare and strange. Astronomy now runs at data scales only machine learning can manage. With more compute, we test broader parameter spaces, run faster simulations, and schedule smarter follow-ups. The pipeline from detection to insight tightens. That shift is mirrored on the policy front. California's AI transparency law requires systems to disclose their non-human status. The core idea is trust built through disclosure. The parallel with science is clear. When claims touch the public square, transparency becomes survival. Institutions must state what is known, what is not, and what comes next, in language people grasp. Right now, 3 Atlas is dimming as it recedes. The window narrows. JUICE may add a piece. Hubble and JWST may add more. Ground arrays keep watching. 2 outcomes wait. Natural yet unusual, which sends us back to improve models. Or artificial becomes plausible, which opens a new chapter. Either way, the process matters. Evidence, methods, and fast, honest communication will decide whether people trust the result. If the verdict is comet, we still gain. We refine models. We tune our surveys. We sharpen our instincts for the next anomaly. If the verdict hints at technology, everything changes. Not only our science, but our self-image. First contact may not be a message. It may be a test of our integrity. Do we report what we see without distortion? Do we stay rigorous under pressure? Do we keep looking when the answer is hard? 3 Atlas will pass on. The lesson should remain. Watch closely. Share clearly. Be ready for the next traveler from the dark. It came from nowhere we expected, out of the deep silence that stretches between stars. No signal, no warning, no arc of radio. Only a faint streak of motion that our instruments caught by chance. As it swung past the sun, the object catalogued as 3I Atlas did something physics didn't predict. It accelerated. The data are clear. The direction of thrust made no sense. No jets of gas. No visible tail. No known mechanism. A push from nothing. NASA's numbers are unambiguous. JPL's navigation models could not fit the motion with gravity alone. The orbit changed in a way that required a continuous, smooth acceleration. Avi Loeb, long criticized for suggesting that interstellar visitors might be artifacts, had described this exact outcome months earlier. He said, "Watch for an object that pushes itself without exhaust. When it happens," he said, "you'll have to ask whether you are watching a machine, not a rock." Many dismissed the idea. Yet the object behaved as if light itself were nudging it along, as if pressure from photons were enough to move it. The effect was small but measurable. In space, small forces rule. Over weeks, a gentle push becomes tens of thousands of kilometers of drift. Its light curve deepened the puzzle. The object brightened 7 times faster than the models for ordinary comets. Its color turned blue, not red, suggesting reflective material. Comets are supposed to look dirty, coated with organic residue and dust. This one gleamed cold and metallic. Astronomers began to divide. The conservative camp said, "Wait. Maybe there is outgassing too faint for our instruments. Maybe its jets point away from us. Maybe the composition is exotic." The bold camp said, "No known comet fits these parameters. A new category must exist, or this object is engineered." The truth might rest in how we measure small details. Perihelion occurred at $1.36, a safe distance from the Sun. Temperatures there vaporize ice but not metal. The radial acceleration measured 135 km per day squared, the transverse 60. Converted to meters per second squared, those values are modest, but sustained over time they reshape the orbit. In orbital mechanics, this is the difference between prediction and surprise. The key instrument, NASA's Punch Wide Field Imager 3, was never built to hunt for alien sails. It was built to study the corona and the flow of solar wind. Yet, by coincidence, it caught 3I Atlas crossing its field. Data meant for plasma research became the seed of a mystery. A navigation engineer at JPL stacked the images, corrected for instrument drift, and found motion inconsistent with gravity alone. When scientists can't explain data, they do not leap to conclusions, they start by testing the instruments. Calibration checks followed. No error was found large enough to account for the anomaly. So the debate moved from hardware to nature. Could a comet lose mass invisibly? Outgassing usually leaves fingerprints, tails, coma, emission lines. None appeared at the required strength. The few gases detected early on, faint water vapor near perihelion, were orders of magnitude below what physics demands to create the push observed. If the acceleration comes from gas, we are missing nearly all the exhaust. That gap is what Loeb calls the silence between forces. You see the effect, not the cause. In every past case, when the cause vanished, something new had to be learned. Color was the next clue. Typical comets scatter light to the red. 3I Atlas reflected blue. Small particles can do that, but only if produced in huge quantities. Without jets, where do those particles come from? The alternative is a reflective surface, metal, composite, something engineered. If you assume such a surface, the radiation pressure model works. At $1.36, the sun's photon flux applies a pressure near 4.5 N per m squared. A surface with a mass-to-area ratio of 1 kg per 1,000 square meters would feel roughly the same acceleration observed. That is a thin sheet, no thicker than a human hair. A sail. If it were a sail, it would not look steady. It would tumble, flash, dim, and flare as it turned. The photometry shows flicker patterns consistent with rotation. Whether random or deliberate, no one can yet tell. Engineers asked another question: what if it wasn't passive? What if it fired an engine near perihelion the way human craft do during gravity assists? The math fits too. A low-thrust ion engine burning for several days could account for the change in speed. But it would require a power source. Solar arrays at that distance could do it if they were large. Nuclear power could do it better. Both options imply design. There is no heat signature yet. JWST's infrared scans in December might find one. If they do, the story changes overnight. The next months matter most. The European JUICE probe will pass within 64 million kilometers, close enough to attempt spectroscopy. Hubble and JWST will follow. If they find gases, the natural model survives. If they find metal lines or unexplained infrared, the conversation leaves astronomy and enters history. Meanwhile, NASA faces questions. Did the Mars Reconnaissance Orbiter's HiRISE camera capture high-resolution images in early October? If so, where are they? Delays are common. Calibration takes time. But in the age of instant speculation, silence reads as concealment. Social networks filled the gaps with conspiracy theories before any data were released. Agencies responded by activating the International Asteroid Warning Network for a coordinated observing campaign routine procedure, yet interpreted by some as secret urgency. In truth, the aim is data, more eyes, more instruments, fewer assumptions. Public attention surged. Podcasts, feeds, news channels all latched on. People asked the oldest question: are we alone? And an even older one: can we trust our institutions to tell us if we aren't? If the object turns out to be artificial, the implications multiply. Governments will seek control. SETI will revive overnight. Missions will be proposed to intercept the traveler before it fades. Philosophers will argue over meaning. Theologians will adapt. Politicians will posture. Every field will feel the tremor. The probabilities remain small but not zero. And that's enough. For scientists, even a sliver of chance demands examination. The trajectory tells us this visitor is interstellar. Its inbound velocity exceeds solar system escape speed. Its path tilts steeply relative to the ecliptic. Models tracing it backward show origins scattered through the galactic disk. It could be billions of years old, wandering star to star. If it is a machine, it is ancient, durable beyond anything we have built. Voyager 1, the fastest probe humanity ever launched, moves at 17 km per s. 3I Atlas moves nearly twice that speed. Something gave it momentum far beyond ours, or it has been drifting for epochs. If it is a relic, then its mission may have ended before our species began. If it still functions, then we are being watched by a survivor older than our civilization. Comparative data sharpen the strangeness. Comet Swan, passing the Sun weeks earlier, behaved perfectly. Gas, dust, tail all by the book. 3 Atlas matched none of it. Same Sun, same physics, different outcome. 2 objects, same epoch, 2 entirely separate regimes of behavior. Photometry tells a story written in light. The object's brightness scales as distance to the power of -7.5. That means it brightened far faster than the energy it received. Reflective area must have increased, perhaps through unfolding panels, perhaps through fragmentation exposing shiny interior. No one knows. Spectra show faint early, then a plateau. Water vapor remained weak. The brightness stayed high. The math doesn't balance. Either our assumptions about cometary dust are wrong, or something else reflects sunlight in ways we've never modeled. The next question is why now? Why in this decade have 3 interstellar visitors arrived: Oumuamua, Borisov, and now Atlas, after millennia of none? Population statistics suggest thousands of such objects move through the outer system each year, too faint for detection until recent survey telescopes came online. Maybe we are finally seeing what was always there. If so, this may be the first artifact we notice, not the last. The data deluge from instruments like Foremost, Vera Rubin, and the coming Roman telescope will flood us with new discoveries. AI systems already trained on millions of spectral profiles will flag outliers before humans blink. Compute power is the new lens. Algorithms will become the hunters of anomalies. Partnerships between AI labs and observatories are blurring the lines between research and computation. The same GPUs that train language models now process terabytes of sky data each night. AI filters sift the noise, looking for movement, color shifts, and curves that don't fit known families. 3I Atlas might be the first case where such a system could have warned us earlier. AI, though, brings its own trust problem. It sees patterns faster than we can verify them. When an algorithm says anomaly, scientists must still ask why. In that gap between prediction and explanation lies both power and peril. In California, a new law requires AI systems to declare themselves non-human when speaking to the public. Transparency by statute. It was meant to prevent deception. Yet the principle echoes across fields: tell the truth about what you are. The same principle may soon apply to science itself. When evidence strains belief, transparency becomes survival. If agencies hide data, they lose credibility. If they release data without context, they spark chaos. The line between caution and concealment is thinner than ever. Humanity now faces twin frontiers. Artificial minds rising on Earth. Possible artificial machines drifting from the stars. Both challenge our definition of intelligence, agency, and honesty. Both test whether truth can survive speed. If 3I Atlas proves natural, we refine our understanding of how matter behaves in sunlight. We add a chapter to comet physics. If it proves artificial, the century changes course. Either way, the way we handle the question will define the era. The lessons are simple and hard. Measure precisely. Publish quickly but clearly. Admit uncertainty early. Never trade accuracy for reassurance. Because one day the evidence will be undeniable, and the only thing left to judge will be our integrity. As of now, 3I Atlas is receding. Its brightness drops each night. Within months it will fade beyond the reach of our largest scopes. If we don't learn enough now, it will vanish back into the dark, leaving only a curve on a graph and an unanswered question. Maybe it was a comet with extreme properties. Maybe it was a machine that once knew purpose. Either way, it came, it accelerated, and it left us with a mirror held to our own curiosity. The first contact, if this was one, did not come with a voice. It came as a problem in an equation, a trace of motion that refused to fit. It asked us one question: when faced with the unknown, will you look away, or will you keep measuring until the truth stands on its own? When the light faded, the arguments only grew louder. Each data release spawned new models, new interpretations, new doubts. Some astronomers insisted that sublimation alone could still explain everything. Others showed the residuals, deviations too large, too consistent. The anomaly refused to shrink. By mid-November 2025, the JUICE spacecraft had completed its long-range scan. Preliminary telemetry leaked through unofficial channels. The signal was faint but intriguing. The spectrum showed reflections peaking near wavelengths associated with polished surfaces, not dusty ices. No clear gas lines. No water signature. No tail. Only reflected sunlight and a geometry that implied flatness. A plane, not a lump. That was enough to reignite Loeb's camp. "This is exactly what we expected from a sail," he said in a late-night interview streamed to millions. "We're not talking belief. We're talking measurements." The comment drew immediate fire from peers who accused him of sensationalism. But privately, even skeptics began rechecking their models. The Hubble team prepared its December window. At the same time, JWST configured its instruments for near-infrared mapping. The global campaign had become a race against dimming. Every hour mattered. The object was already past its brightest phase. By January, it would be gone. Inside control rooms, the tone had shifted. Nobody used the word alien. They spoke of non-gravitational dynamics, reflective efficiency, unknown momentum sources. But everyone knew what those phrases meant between the lines. The Hubble images arrived first. Pinpoints of light arranged in a shape slightly elongated, not spherical. Some researchers thought they saw periodic flickers, rotation every 6 to 7 hours. Others said the data were too noisy. The press demanded answers. NASA released a careful statement: 3 Atlas continues to display anomalous motion not yet fully understood. Additional observations are under analysis. JWST's results followed days later. Its sensors detected a thermal imbalance, parts of the surface warmer than expected, as if heat was being released from within or from specular reflection concentrated on certain facets. The excess was small but statistically real. It could mean layered metal. It could mean power. Social media erupted. News banners declared artificial object in solar system. Hashtags trended. Governments issued no comment. In scientific forums, caution ruled. Extraordinary evidence, they repeated, requires extraordinary verification. Verification came slowly. Teams in Chile and Hawaii attempted follow-up spectroscopy. They confirmed the blue hue. They saw no gas. They recorded steady dimming consistent with a solid body reflecting sunlight. At that point, the discussion moved beyond astronomy. Policy advisors from several nations met quietly with NASA and ESA representatives. Contingency briefings circulated how to communicate potential extraterrestrial evidence to the public, how to coordinate messages, how to prevent panic. It was uncharted ground. Loeb, now at the center of global attention, argued that the best defense against speculation was openness. "Release everything," he said. "The public can handle ambiguity. What they can't handle is silence." Some agreed. Others feared chaos. Within universities, the debate turned philosophical. If the object was artificial, then by definition it was a message, though one without words. A message written in trajectory, in acceleration, in silence. Was it a relic? A probe? A grave marker of a lost civilization? Or a test of ours? Graduate students built simulation after simulation. Could fragments of a millennia-old sail survive interstellar erosion? Could micrometeorite impacts produce the observed flicker? Could unknown volatile chemistry mimic metallic reflection? Each model solved one problem and broke another. By February 2026, 3I Atlas had faded below magnitude 25. It was gone to our eyes. Only telemetry and archived data remained. The working groups compiled their final reports. None dared use definitive language. Every conclusion carried caveats, possibly inconsistent with known comet behavior, suggestive but not conclusive. Yet between the lines, a pattern emerged. No visible outgassing. Unexplained acceleration. Reflective, blue spectrum. Flat geometry. Warm anomalies. Taken together, these defied natural explanation. Public trust became the next frontier. The press demanded full data dumps. Independent analysts pored over the raw frames, reproducing NASA's results. Nothing changed. The object still looked unnatural. Then the politics began. Some legislators called for a dedicated mission to intercept future interstellar objects. Others called for restraint. "Don't provoke what we don't understand," one senator warned. The phrase cosmic caution entered public vocabulary. In research circles, attention turned to probability. If one interstellar object in 3 showed anomalous behavior, what fraction of all such visitors might be technological? Even a fraction of a percent would mean thousands crossing the galaxy at any time. Funding shifted. SETI budgets expanded. New telescopes were proposed, ones optimized not for signals, but for motion. Light curve anomaly detection became a discipline of its own. AI systems were trained to flag any deviation from gravitational norms. In laboratories, engineers began discussing what an intercept mission would need. High-velocity propulsion. Autonomous navigation. Rapid response. Within months, 3 design concepts were on paper. None could reach 3I Atlas, it was already too far, but all could chase the next one. As months passed, attention faded. The world moved on. But in observatories and think tanks, the files remained open. Every data point of 3I Atlas became a benchmark. Every new comet was measured against it. Each time the numbers matched expectation, scientists relaxed. Each time they didn't, old questions stirred. By late 2026, the official line held, "Natural explanations not yet ruled out." The unofficial consensus whispered otherwise. "We saw something we don't understand," one senior astronomer said quietly, "and it behaved as if it knew how light works." Years from now, students will read about this object. They will see it listed in tables as an asterisk beside 2 names, Oumuamua and Borisov. They will learn about acceleration vectors and photometric anomalies. But they will not feel what it was like to watch it live, to see the graphs shift in real time, to feel the weight of uncertainty pressing on every calculation. Because 3I Atlas did more than defy physics. It changed how science communicates the unknown. It forced institutions to confront transparency in a world that demands instant answers. It made the public a participant in discovery, whether scientists liked it or not. When the story of first contact is written, it may not start with a handshake or a transmission. It may start with this: a faint blue object that sped up for no reason anyone could find, passing silently through the light of our star, then fading away. It left no message, no code, no evidence of intention, only data, and the reflection of our own need to know. The real discovery was not in the object but in ourselves. In how quickly we rallied telescopes, how fiercely we argued, how deeply we cared. 3i Atlas tested our science, our institutions, and our honesty. It asked a question that still echoes in every lab and every observatory. When the universe shows you something impossible, do you cling to what you know, or do you let the unknown reshape you? Perhaps that was the message all along.